Hi everyone, I'm from Text to Speech. On behalf of Manuel Serrano, I'm going to present the paper titled Of JavaScript Ahead of Time Compilation Performance. JavaScript is particularly difficult to implement efficiently, because most of its expressions have all sorts of different meanings that involve all sorts of different executions that are not distinguished by any syntactic or type annotation. Let's illustrate this with this simple example. Most C programmers would know that this loop is compiled with a couple of registers and a conditional branch. But what if we are now turned into JavaScript programmers? This is a all different story, because it all depends on A can be an array as before. But it could also be an object, provided it has properties named length, 0, 1, and 2. A could also be a sparse array, or even an array with one property holds by its prototype. Even worse, if we modify the increment, the loop can also be used with radically different indexing. The difficulty is there. The same code can be used with many different data structures. So this raises the question: does it make any sense at all to try to compile statically such a language? Or even more fundamentally, why trying? There are actually several motivations, incentives, and reasons. First, hardware constraints that prevent us to use JIT compilation. Second, brief executions for which JIT are probably not beneficial. Third, because this is an intriguing research question. Is it possible to build fast JavaScript ahead of time compilers? How fast can they be? So, how to attack the problem? First, by deploying conventional compilation techniques. And, second, by accommodating just-in-time compilation principles to ahead-of-time compilation. The idea is to rely on optimistic compilation. Let us illustrate this principle with the fib function. The fib function will be compiled into three functions. First, a dispatch function that will branch according to the type of the argument. Second, two versions are generated. One specialized version, above with a green mark. One generic version, below with a red mark. The specialized version, specialized for integer arithmetic in this example, is much faster than the generic version because it uses faster operators that do not check the type of their arguments. The central question is how to select the types of the specialized versions. This has been the subject of previous studies of our own. Our proposal is a departure from traditional type inference systems. Instead of trying to infer types according to all possible executions, types are inferred according to efficiency criteria. That is, the compiler assigns variable types that enable the better code generation. Our approach relies on the following assumption. The most likely data structure a program will use is the one for which the compiler is able to produce its best code. This is an effective approach because it successfully assigns relevant types to variables and functions. Also, because specializing for types that would not yield better code generation would be pointless for optimization. To validate the approach, we have built hop.js, an ahead-of-time compiler for JavaScript. Hop.js compiles all of JavaScript, but it does not optimize the whole language. Some features and some library functions are not optimized. For instance, directival, or floating point numbers. Remains one major problem. JavaScript is a big language. How to cope with such a large language, for an academic project, managed by a single researcher? The solution has been to compile to another high-level language. Because of the proximity of the two languages, hop.js compiles JavaScript to Scheme. The generated Scheme programs are then compiled into C. These C files are then eventually compiled to object files or shared libraries. In spite of their proximity, JavaScript and Scheme have significant differences. In this talk, we present two of them. JavaScript functions and Scheme functions are different. Scheme functions are read-only values. JavaScript functions are regular objects that can be extended with new properties. Let us start studying the implementation of the scheme function. It uses two free variables, c and base. The variable c is assigned, so it is boxed. It is compiled as shown in the figure. The function is implemented as one heap allocated object, and one heap allocated box for c. Now JavaScript functions. Here is the similar function implemented in JavaScript. Because it is a regular object, its implementation is more complex than the plain scheme implementation shown in the figure. In addition, extra values are allocated. Obviously, JavaScript functions are much more expensive than scheme functions. To mitigate the problem, we use ad hoc compilation patterns. We present in this slide the one used to compile for each, a library function that applies a function to all the elements of an array. Instead of passing to for each a fully built JavaScript function, we pass it a stack allocated scheme function. If the array is a plain array that do not override for each, the scheme function is used. If the array overrides for each, the full JavaScript function is allocated and the plain generic for each function is invoked. This is the purpose of the JSArray for each function. It first checks if this argument is a plain array. If it is, it calls JSArray for each procedure that works with scheme functions. Otherwise, it heap allocates the JavaScript function and calls the standard for each function. This is another illustration of the optimistic principle. Here, we assume that for each is the regular JavaScript for each function, so we speculate that there is no need to build a full-blown JavaScript function. Let us mention another important difference: numbers. Contrary to most general-purpose programming languages, JavaScript only supports floating-point numbers. However, integers play an important role, for instance, for accessing arrays. So the question, how to represent integers? And more precisely, in our case, how to map JavaScript integers to scheme integers, there are at least 4 known possibilities. The simplest solution could be to represent all numbers, including integers, as floating-point numbers. We are not aware of any system designed for performance that uses this strategy. The second possible strategy is nantagging, a technique that takes advantage of all the possible not-a-number values to encode type information. The remaining options are to distinguish integers and reals values using bit patterns. Floating-point numbers are heap allocated and integers are represented as 32 or 53-bit values. We have implemented the last 3 strategies in our scheme implementation and we have measured the performance differences. Unsurprisingly, nantagging outperforms all other encoding for the ALMA benchmark as this program uses floating-point numbers intensively. Nantagging saves the heap allocations the other encodings use. Unfortunately, we have not been able to obtain competitive performance for the other tests. This is why hop.js does not use nantagging. We must note that this might be due to an insufficiently polished implementation, as some industrial JavaScript implementations use this encoding, with apparently much more successes. The 2 other frameworks, SMI and Int53, deliver close performance but with an advantage to Int53. This is because Int53 takes advantage of some IEEE 754 peculiarity. Above 2 to the 53 only even integers can be represented. In consequence, Int53 values that are simply incremented never needs to be transformed into floating-point numbers. This characteristic does not hold for the SMI representation. Let us now present some benchmark results. Jetstream used to be a popular JavaScript benchmark suite. We have compared the performance of hop.js with the performance of node.js, that relied on V8, with the performance of SpiderMonkey, named JS68, used in Firefox, and with the performance of JavaScript Core, named JSC, used in Safari. The first observation is that hop.js is about 1 order or magnitude slower than all of the other systems for all floating-point intensive programs such as Crypto, InBody, or Raytrace. Hop.js also performs poorly on DatesParb, but this test uses IVL, a feature hop.hs does optimize at all. The benchmark Delta Blue also exhibits a pathological performance problem. For the other tests, hop.js is in between 1.5 times and 3 times slower than the competition. This might be regarded as a weak result, but we have to observe that all systems but hop.js have been using Jetstream for decades, and as such have spent decades optimizing these very benchmarks. It is then questionable whether these tests are still representative of these systems' performance. For this reason, the major JavaScript implementers have decided to retire Jetstream. This is why we are proposing another benchmark suite that, we think, better approaches JavaScript server-side usages, the application domain targeted by hop.js. Hopstone is composed of 18 benchmarks. In the interest of time, we use only 16 in this presentation. The tests are coming from different sources and they are implemented by different authors. Instead of presenting the peak performance of each system for each test, we show curves that indicate how systems perform when inputs grow. We think this visual representation better shows the general performance of each system. It would probably be unsuitable if we were interested in comparing few percentage differences, but here, we are only interested in comparing the global performance of each system. The first observation is that which system performs best varies from one test to the other. The second observation is that apart from a bench that we have already mentioned, hop.js is competitive. For most tests it delivers performance comparable to those of industrial JIT compilers. Let us zoom in some results. BAG and BASIC show that hop.js handles efficiently integer arithmetic and simple array accesses. Laval, which uses higher order functions, shows that, in spite of the complex encoding of functions, hop.js is competitive for allocating and using closures. Marked, which is a markdown parser, shows that although not highly polished, hop.js implementation of ropes delivers decent performance. Minimalist execution is dominated by arrays obtained by splitting strings. Most of these arrays have very brief lifetime. This pattern is not handled very efficiently by hop.js that uses a conservative non-copying garbage collector. Moment is a library for dealing with dates for these operations. Hop.js rests on POSIX functions operations that relies on set. This is not competitive with a native implementation. Richard's proxy is the only test that uses proxy object. This test shows that hop.js is competitive even for tests that use high-level JavaScript features. UUID uses exceptions. The hop.js implementation that rests on set jump, long jump, is not as fast as the compared Git compilers. The paper contains analyses of the other tests. In conclusion, the paper presents hop.js, an ahead-of-time compiler for JavaScript. The paper shows the principal aspects of the compilation from JavaScript to Scheme, and it shows the ad hoc optimizations that have been added to the Scheme compiler in order to improve the performance. The paper presents two benchmark results. It presents Jetstream, is an old JavaScript benchmark suite, for which hop.js is slower than industrial JIT compilers. It also presents Hopstone, a benchmark suite composed of various tests, among which some are currently used in the wild. For the second test, hop.js shows competitive results. At this point, it is still difficult to conclude if ahead-of-time compilers can or cannot reach the same performance level as JIT compilers. It is difficult to understand if the weak performance of hop.js on Jetstream are due to the over-optimizations of JIT compilers, or to intrinsic weaknesses of the ahead-of-time approach. You will probably have to make your own opinion. Unsurprisingly, we believe that Hopstone is more representative than Jetstream because Hopstone is composed of programs actually used in real applications. We see the results on the Hopstone suite as a strong incentive for continuing the exploration of ahead-of-time compilation of dynamic languages such as JavaScript. Thank you for your attention.